Welcome to our final review. This video will go over review number 6 for our AP Statistics exam, hypothesis or significance tests. This covers pretty much chapters 9, 11, and a little bit of 12. So here we go. Significance test, a procedure that provides evidence for or against some claim using sample data. We wish to estimate a parameter. We use a confidence interval, but if we're trying to test a claim, right, that's big here. If we have a claim, we use one of these tests. And we have all sorts of tests. We've used one sample t-test for mean, two sample t-tests for the difference of mean, matched pairs t-test, which is the same as a t-test right there. One prop z test for proportion, one proportion. Don't say z-test. This is a one prop z-test. So this one is really important there. And two prop z-test for P1 minus P2. Chi-squared goodness of fit, GOF. And chi-square test for homogeneity and association. Those use the chi-square test with matrices, if you're ever to do one of those on your calculator. And then there's a slope test, Ling-Reg t-test. You can see all those again in your menu. So let me quit on that. Here we're going to go to stat, tests, and all of your tests here, your t-test is 2. Two sample t-test is 4. So let's write that down, 2, 4. That's 2 again. One prop z-test is going to be 1. Two prop z-test is going to be 6. Excuse me, not 1, 5 and 6. And you can go through the rest here. Chi-squared goodness of fit, chi-squared. All the chi-squared ones are down here. There's a goodness of fit and just chi-squared test. So both of those are there. And if you do need a Ling-Reg t-test, which you probably won't, it's down there at the bottom. So I guess that'd be D and C. D and C. So those are in your stat menu for test. We'll get a little bit more into them as we move on through this review. The general formula for a test statistic is statistic minus parameter over standard deviation. It's kind of like a z-score formula, but this is generic, right? So some number minus your parameter, which could be like your true mean or your true p or your true slope or whatever, over your standard error, standard deviation, and statistic. And we follow that 4-step plan just like for intervals. So we do state, plan, do, or conclude, or the pass, parameters, assumptions, always include your alpha. Parameter procedure, always include your alpha, your assumptions and conditions, your statistical work, and summary statement. We either fail to reject or reject the null in context of the problem. And that part's important. So make sure you do the 4 steps when asked to test a claim. For your hypotheses, you want to assess the evidence produced against data against a null. A null is the no difference, right? So that's going to be like, it's always going to be equal. And the alternative is if it differs. So it could be less than, it could be greater than, or it might simply just be not equal. And that we call a two-sided test, where the other one is going to be one-sided. So always define your parameters in context of your hypotheses. Again, I'm going to say context usually. And a significance level is provided, stated, but typically 5% is your default. So if it doesn't say 1, use 5%. And ultimately, we're trying to see if we can reject the null and conclude that the alternative is correct. So our goal in it is always try to conclude the alternative. That's the goal. So when we do our conditions, they're the same conditions we did in review 5. So if you want to see review 5 for all those conditions, there's a random, independent, normal. For chi-squared, random, independent, large counts, meaning 5 or more. And the line error again, linear, independent, normal, residuals, equal variance, and random. And you can see review 2 for those. So I'm not going to go over those again. Those are your conditions. Always state those in your write-up problem under your assumptions. Your calculations, you're going to choose the appropriate test based on the problem. So it could be a a proportion. You'd use Z. We got zap tax, right? So proportions use Z. Two proportions use 2 sample Z. Means use T. So your test statistics either going to be a Z, T, or chi-square depending on the test. Degree of freedom for T and chi-square is for T and chi-square test first. So for T is always going to be n minus 1. And then degree of freedom for chi-square test depends on the chi-square. We'll get more into that in the next couple things here. But the degree of freedom for a chi-square test, if it's not goodness of fit, it's just the row minus 1 times the column minus 1. And I'll talk more about that when we go over chi-squared. We want to compare the p-value to alpha. So we either state the p is greater than alpha or less than alpha, and we have a conclusion. So if p is less than alpha, we reject. We have sufficient evidence, statistically significant is a word we use. So statistically significant. So we can make a conclusion, right? We say we can conclude the alternative in context of the problem. So small p-value, we say we have evidence to conclude that the alternative is true. And if the p-value is large, greater than alpha, we fail to reject. We never accept the null, we fail to reject. That's important. So we do not have convincing evidence. There is not convincing evidence in context of the problem. We never say accept. We say we fail to reject the null. We just can't prove the alternative. And it's the whole innocent until proven guilty thing, right? That's kind of the whole purpose of a significance test. So let's talk about p-value. It's basically the likelihood of getting an observation of a sample as extreme or even more extreme from the value of the parameter by chance alone. Under the assumption, and this is the important part, that the null is true. Because we have to assume the null, right? So assuming that the null is true, you get an observation that's extreme, a really extreme, that p-value is going to be small, right? If it's not super extreme, it's going to be the likelihood of that happening is pretty high. But if it's far out there, you got your null here, and you got your sample out here, and you're trying to see, oh, is there anything at that point or greater? That's going to be a small p. But in this case, if you got your null here, and you got your sample, let's say here, well, that's a little bit bigger, right? So your sample there, your statistic is the p-value is going to be greater than your alpha in most cases. So the further away from the null, the more likelihood that you're going to reject the null hypothesis because that p-value is so small. It's not going to happen. Not very likely it's going to happen. You can make errors, of course, when you can reject the null when it's true. And you can fail to reject the null, fail to, right? Fail to type 2. So type 1 is reject the null when it's true, defining context. Type 2 is fail to reject the null when the alternative is true, or when HO is false, is another way to say it too. In your conclusion, if you reject the null, then the only possible type of error you could make is a type 1. If you reject the null, you could make a type 1 error. You can't make a type 2 because you haven't failed to reject it. If you fail to reject it, then the only possible type of error you can make is a type 2. Okay, so read through that real carefully. And the probability of making a type 1 error is always your alpha level. So probability type 1 typically your alpha, which is typically about 0.05, excuse me, 5%. All right, now let's talk about power. In general, we don't have to get too technical here, but power is when the test gives you better conclusions. That's generally what you're looking for. So power test against a specific alternative is the probability the test will reject the null at a chosen significance level A when the specified alternative value of the parameter is true. In other words, it's 1 minus the probability of type 2 error, but we don't have to get into that. If you increase your alpha level, it increases the power. If you increase the sample size, increase the power. If the actual parameter is farther away from the null, when the alternative is true, it's a powerful test. So just think logically here. If you have a null hypothesis of whatever, and your actual parameter is out here, and you conclude out here, yay, I've concluded out here, then it's powerful, right? But if it's closer here, it's not as powerful. So the further away it is, it's gonna be a more powerful test. So don't get caught up over the formulas and stuff like that. It's not really that important. Just think about it in common sense wise. Bigger sample size always is better, right? You want n to go up, and you want that parameter ideally to be farther away because you're trying to test against the null. So you want that to be out here. Here's a whole slew of different types of hypotheses. I'm not going to sit here and read all these, but you can read through these and see. These are just examples. But one common thread for all these is all the nulls will always be equal, right? So it could be one sample mean, two sample mean, match pairs, the difference, proportions for one proportions, two proportions. Notice that they're all parameters. So we're not going to use like x bar is equal to 0. It's mu is equal to 0, right? We're not going to use p hat equal 0.8. We're going to say p equals 0.8. And there's nulls for chi-square tests, but they're a little more generic. Just the actual proportions are the same as stated proportions for goodness of fit. Whereas the alternative is just different. Chi-squared, the distributions among whatever are the same. Distributions are not the same. Remember, chi-square test for homogeneity is if it's multiple samples. Where if it's independence or association, it's just one sample. And these are your matrix. Chi-squared tests here are your matrix one. And for slope, it's just the nulls, there's no linear relationship. So slope is 0, whereas there is a linear relationship. But of course, you could have a one-sided one here. So you could say less than 0, negative linear relationship, or you could say greater than 0. So there's all sorts of different alternatives you can have, but the null is always going to have an equal. Okay? So let's talk about chi-square. Chi-square test. Observed minus expected squared over expected. This is on your formula sheet. And because it's on your formula sheet, you're probably not going to need to use it, right? Because a lot of times that stuff's given to you. But there is a formula: observed minus expected squared over expected. And remember that if it's a goodness of fit, it's one variable. We're trying to look at all these different proportions. Your degree of freedom is going to be the number of categories minus 1. If it's association, independence, or homogeneity, your degree of freedom will be in a matrix. You got a number of rows here and you got columns here, and you just subtract 1 from each and multiply them. And the difference between association and independence is you have multiple variables, right? You're trying to make a comparison. And you only have one sample. Where homogeneity, you're looking for distributions. And you're trying to see, is the distribution among one sample different than among the other samples? So you're gonna have two or more samples on that, but it's still one variable, distribution of these, color scheme or whatever. And there is a chi-squared CDF. I will show you how to do that real quick if we need it. Chi-squared CDF is going to be second vars, and it's going to be down here, 8. And your lower is always going to be 0. We just leave it at 0. Or actually, the lower would be whatever the chi-squared test statistic is. So let's say your chi-squared test statistic is 3. Your upper is just going to be infinity. So you just do 1E99, just like normal CDF. Degree of freedom is the number of categories minus 1. So let's say it's 4. And there's your chi-squared. And the larger the chi-squared, the smaller the p-value. You want to know why that is? That is because your chi-squared is a right skew distribution. And if you get a chi-squared test statistic way out here, it's going to be smaller p-value. But guys, chi-squared is larger in this direction. So larger the chi-squared test statistic, smaller the p-value, we would reject the null. So this 10,000 is, you can just use 1E99 if you want. That's infinity to find the p-value. All right, let me pull that off here. All right, so for goodness to fit, you're going to enter all your counts in L1. So if you have like a set of data here, let's do an example problem. So let's say you have a bag of M&Ms, like 5 of one color, 7 of another color, 4 of one color, 3 to 2, whatever. Find the total in sample size, enter the expected values, total sample size multiplied by each category's probability in L2. So let's say you add all these up, 5, 6, 7, 8, 9. 9 plus 7 is 16, plus 5 is 21. Let's make that an even 20 by making that 6. Okay, so let's say it's out of 20, and out of that sample size, the expected value would be what those probabilities should be. So let's say it's supposed to be 5 or 4. Let's say they're supposed to be in equal amounts, and these are the differences, right? There should be 20 there and 20 there. So what we're going to do for a chi-squared goodness of fit test is we would go to your test here, go down to chi-squared GOF. You have L1 and L2, and your degree of freedom here would be 4, because I believe I put 5 categories in there. And I'm going to go down to calculate. And you can see my p-value is super large because my numbers really weren't that different according to my sample size. So that's how you do that. So you're going to have a TI 84, so don't worry about the 83 here. So larger p-value, larger chi-squared, smaller p-value. And in this case here, a smaller p-value means you reject the null, which means that we can conclude that the proportions are different. All right. Let's talk about chi-squared homogeneity. Now for these ones, it's all about the matrices. I'm gonna pause this to plug in my computer. All right, like I was saying here, it's all about matrices on these if you actually have to run a test here. So let's refresh on how to enter a matrix. If you need to enter a matrix, you go to second, x to the -1 power. go to edit, and you throw in whatever matrix. So if you want a 3x4 matrix, let's do a 3x2. So you just put the numbers in as you see them. So whatever the numbers are, throw those in there. That's your data, right? These are your counts. And then you're going to go to stat, test. You're going to run a chi-squared test. Not goodness of fit, just regular test. And you're going to go down to calculate. And it's going to throw all that. Again, I just threw random numbers in there, so your p-value is really high. But there's your chi-squared test statistic. Notice that's pretty low, small, high p-value. But then if you want to get your actual your expected values, you would just go to second matrix and go down into there, and those are the expected values right there. Okay. And again, if you're trying to get expected values by hand, if you got a matrix, let's say it's 3, 5, 8, 2, 7, 4. To get the expected values by hand, you just do your totals. Never actually put your totals in a matrix, but I'll show you how to do one. So that's going to be 5, and that's going to be 8 plus 8 is 16. So to get the expected values, you would just do observed, or your row total times your row column divided by your overall total. So for the expected, you would do, in this case here, 16 times 5 divided by however many there are here. So there's 5 plus 12, 17 plus another 12. So it's going to be 29. So it's going to be 5 times 16 divided by, what did I say? 24 plus 5, 29. And whatever that number is going to be expected. So I'll do that 1 here so you can see. And that would be about 2.76. And then you do that for all of those rows times column total divided by overall. So that's what that is. And if you want to see that actually, let me erase my memory. 2nd plus 7, 1, 2. If you want to see that actually in practice, let me do that here. So I'm going to do a matrix, go to edit. And let's put those numbers in. This is a 2x3. So 3, 5, 8, 2, 7, 4. And let's run a chi-square test. Stat tests go up. And let's put our expected in B again. And we'll calculate it. And you can see our expected by going to second, x to the negative 1, option 2, and there's your 2.75 right there, 76 right there. So that number there is 16 times 5 divided by 29. When you're doing your chi-squared test, remember your random, independent, and large expected values. Large counts are expected values greater than or equal to 5. That's kind of the rule there. All right, let's see what else we got. Lin-Reg t-test, man, you can go back to review 2 for that. I'm not going to really get into those because you don't really see those a whole lot. So that should conclude our review. Go ahead and work on the multiple choice. And if you have any questions, please let me know. I want to be of any help as I can. Take care, guys.